Yes,
Just
yes.
give me 2 minutes, Sapna.
Okay.
There is some problem with the title here. And
Ma'am, we are going live from my side.
acha, okay. Then I will not try.
Okay.
Yeah.
Yeah, the message is coming. My meeting is now streaming online, live on YouTube.
Okay.
All right.
Okay.
So I think we should start now. Sir, can we start?
I am ready. Yes.
Please.
Right. Then okay. Then so good evening, everyone. So once again, with great enthusiasm and joy, I extend a heart. Message is coming. My meeting is now streaming online, live on YouTube. Okay. Right. So I
Sir,
think
sir, live mute. You have to mute live. There is an echo.
Done.
okay. Right. So I extend a heartfelt welcome to each and every one of you who has gathered here for the 17th lecture of our ongoing series on physics education research. I'm delighted to extend a warm welcome to our esteemed president of IAPT, Professor P.K. Ahluwalia, as well as Professor Govind Lokhotia, who will preside over today's session. I would like to extend my warm welcome and greetings to Ma'am Rekha Ghorpade, the Secretary of IAPT, and our distinguished speaker for today, Mr. Robert Grover. A warm welcome is also extended to all the esteemed members of IAPT who have joined us. The title of today's talk is Databot, a new paradigm for sensors in physics education. Databot, developed by Robert Grover, is an innovative educational tool designed to enhance the teaching and learning of physics through real-time data collection and analysis. So by integrating various sensors, Databot enables students to engage directly with physical phenomena, allowing them to gather empirical data during experiments. So I'm sure we all will enjoy this enlightening talk. So I'm pleased to introduce Dr. Govind Lokhotia. He is an accomplished assistant professor at Bajaj College of Science in Wardha, Maharashtra, where he has been shaping young minds for over 11 years. Dr. Govind has dedicated himself to providing high quality education in physics, fostering a deep understanding of scientific principles among his students. And in addition to his teaching role, he served as the honorary director of the Bajaj Science Center, where he designed and implemented academic programs aimed at experimental learning for school students in the Wardha districts. Dr. Govinda's academic journey includes a research project at Indian Institute of Technology, Kharagpur, where he focused on piezo resistors and pressure sensors following his work at CMET in Pune. With a blend of practical experience and a commitment to educational innovation, Govind Lokhotia is a valuable contributor to the field of physics and an inspiring educator. We welcome you, sir. So before we start, I hand over the mic to President P.K. Ahluwalia to give his opening remarks, and then Dr. Govind Lokhotia will take over.
So thank you very much, Sapna, and welcome, Robert, to this very interesting program on a topic which is very much talked about in the country. We have, for example, Dr. Satya from Inter-University Accelerator Center, who is working in this area quite a bit. And I looked at Professor Robert's work which he has done. It's just astonishing, amazing work which he has done. And I'm sure that with this lecture, we will get initiated into what he has done and how he is actually taking this as a very interesting input for physics education itself. I felt that Robert has a lot of interesting ideas also on monitoring and maybe assessment of physics education of these kinds of programs. So I'm sure that we will definitely get enlightened about both technology and its impact on physics education itself. So thank you, Robert. Once again, welcome.
Thank you.
So thank you, sir. So now I request Dr. Govind Lokhotia to take over and start the session.
Thank you, Dr. Sapna. Good evening, everyone. It's my privileged to chair today's session in our IAPT's PR lecture series. And yes, it is my honor to introduce a senior leader in the field of STEM education, Mr. Robert Grover, the CEO of Databot, a US-based company. Mr. Grover holds degrees in creative writing and business management, which complement his vast experience in curriculum development, product design, open source hardware and software, and yes, innovative business models also. His unique blend of skills equips him to navigate the complexities of education and technology seamlessly. Mr. Grover has dedicated nearly 30 years in advancing STEM education, having held various position roles, including STEM educator, CTO, executive vice president, and CEO of his company. His extensive experience and leadership in this Databot industry, in the STEM industry, have undoubtedly shaped the way educators and students interact with science and technology. Under his guidance, Databot has emerged as a revolutionary tool that inspires students to explore science and technology through innovative sensors and software. This engaging approach not only makes learning fun, but also brings the invisible world of data to life for young learners. Today, he'll be sharing the body of research, tools, and curricular approaches he and his team utilize to optimize student engagement and improve student comprehension of important concepts. A number of use cases will be introduced, and a free lesson unit and software resource will be provided for participants to take back to their classroom for immediate implementation. So please join me in giving a warm welcome to Mr. Grover. I request Mr. Grover to enlighten with the features of his fantastic Databot, which is a tiny wireless multi-sensor device. I request Mr. Grover to start the session.
Well, thank you very much for the introduction, and thanks for having me this evening. It's morning here. The sun's not quite up yet, but I've had enough coffee that I think I can probably carry an hour. So what I'm going to do here is share my screen, and we'll just get started. And there we go. Is everybody seeing my presentation okay? You should see a welcome screen for Databot.
Yes.
Great. Okay. So Databot, as you mentioned, it's really an interesting device. So as you had mentioned, I've had over 30 years of experience in STEM education. I started before it was even called STEM, frankly, and that was in an after-school program when I was fresh out of college. We were teaching kids how to do Lego robotics, teaching them how to do electronics, engineering with Legos. And this was in 1988. So this dates me a bit, but I've been doing it a while. So over the past 30 years, I've seen many, many different types of approaches, done lots of robotics, lots of hands-on projects that ranged from, everything from, again, electronics to architecture to hands-on life science. And one of the things that stood out to myself and my co-founder for Databot is that, lots of things especially for early education experiences for kids who are younger. A lot of those are too complex for educators to implement without a lot of technical training and a lot of equipment and things like that. Just becoming prepared for doing Lego robotics, for example, takes quite a bit of training. What we wanted to do was come up with something that was very friendly, and I use the term friendly and approachable and comfortable. I use those terms a lot because that's what we're striving for. We want kids to find this interaction with sensor data to be as comfortable and easy as, using a pencil. And so that's why Databot is so tiny. First of all, it's very small, it's very portable, it's easy to take into remote places. You don't have to carry a lot of equipment, but with it, it brings a tremendous amount of opportunity for teaching. And I think this picture with this student right here is a perfect example. You can just see that she's not intimidated by the device. She's doing an activity called a steady hand, which is from our Ninja Physics lesson unit, which you're all going to get to try today. So you'll be able to see this, hands-on, and it's something you can actually take back to your classrooms as well. Anyway, Databot is a teeny tiny science lab, basically. It's got 16 sensors that come with it. 15 of those are built in to the Databot itself. And it allows you to very easily and quickly connect to those sensors using an app and start experiencing that invisible world of data that surrounds us. Now, when we put Databot together, we of course looked at the research that's out there, and sensors in the classroom have been around, for many decades. So there's a tremendous body of research that's out there that supports their use. And I'm sure many of you are using, probeware for maybe Vernier or Pasco or data harvest. There's many different types of sensors that are out there. And, the research that has come out of that is tremendous. And one of the things that I like to draw attention to, and in fact, after this online workshop, what I'm going to do is share this full document with you. But this is a research compilation of a number of studies that talk about how sensor use in the classroom, can benefit students. But one of the quotes that I draw from is this one up here, because this to me is one of the most important and the one that I see pretty much daily when I work with kids. So the quote, "The findings revealed that only the simultaneous display of real-time data resulted in significant learning, thereby emphasizing the importance of immediate feedback through real-time data display for the effective comprehension of graphically represented scientific concepts." Now, what that means is that instant feedback when you're working with data makes an enormous impression on students and seriously increases the level of comprehension of scientific concepts. Now, I always give this as a very simple example, and I typically do this when I first introduce Databot to students or our educators when we're doing workshops. On the left-hand side, you can see Databot being held there by a couple of fingers. And on the right-hand side, this is a screenshot from our app, Visi, which you're all going to get to try today. But, the difference between having that immediate feedback and talking to somebody about something that's in a textbook is extreme. We've all talked to kids probably about, okay, we exhale carbon dioxide. We take in oxygen, we exhale CO2. We talk about that a lot in life science. We experience that on a daily basis, but there's a big difference when you hold the Databot out to somebody and you ask them to breathe on it, and they're looking at this screen and they see this immediate spike when they exhale. And in fact, I usually see even educators will just, they'll back up and say, wow, because it's so fast and so responsive. So the difference there is, wow, we can see that we exhale CO2. And then you start working with kids, and this is our approach to activities that I want to emphasize, because you're going to get to experience this today. But you start talking to kids about the data that they're seeing, and we talk about, well, what can we do to maybe change that data or work with that data? And of course, exhaling carbon dioxide, what can we do with our physiology to increase that level? And kids, through discussion and talking about how your body works, we come to the conclusion, wow, maybe I could hold my breath and get a bigger number, which they do. And then it's a very natural occurrence for kids to start exploring data. It'll evolve into a competition, who can get to the highest level of CO2. And the app is so easy to use, which again, you'll get to see here shortly. But you can tap on that graph that you see, and you can zoom in on data sets. You can pan through them. You can tap on data points very easily, and you can see, exactly, okay, right there, I had, 5,000 parts per million. So, that's my highest score. But again, that word comfortable, we're attempting to create an environment where it's extremely easy for kids and educators to explore data sets. So there's not a lot of cumbersome material around it, wires and things like that. It's just you tap on an icon and you're connected to data and you can start doing experiments. So a quick look at Databot. On the right-hand side, you'll see all of the sensors that are listed. And for physics, there's obviously an awful lot of opportunity there. You've got an accelerometer, you've got air pressure, you've got light, you've got color, you've got a gyroscope, you've got a magnetometer, you've got proximity sensors, sound, temperature, ultraviolet light. So lots of different things that you can explore just in the palm of your hand. I'll give you a quick tour here of just where some of them are located. We won't spend a huge amount of time going through the product itself because we want to get to the actual activity where you're going to be able to use the app. But I'll give you a quick tour of where some of these live. So for example, starting with the accelerometer, here in the center, you'll see a little label called IMU, which of course is your inertial measurement unit. So that center module has your accelerometer, your gyroscope, and your magnetometer. Now, a few examples of how we use this with kids. We have an activity set called, again, Ninja Physics, which you're going to try today using just your smartphone. But we use the accelerometer on the Databot, and I'm going to hold it out here in the palm of my hand. We have something we call home position. So when kids are using Databot, the first thing we do is really orient them. So physically, they have a reference point. Home position has the power port pointed back towards me, which is this here. And then once I have it flat in the palm of my hand, I can reference things like the Cartesian coordinates. So side to side is the x-axis, forward and backward is the y-axis, up and down is the z-axis. And you'll be able to visualize all that in the Visi app. Today, when you're going to do this steady hand activity, which that first picture I was showing, you're going to be trying to focus all of the force of gravity, 9.8 meters per second squared, on the z-axis of your smart device. So you'll be able to see this. But again, the portability and size of Databot allow you to do lots of interesting activities. With the gyroscope, for example, we have a series where we introduce kids to rotational speed and just have them do things like put the Databot on the top of their head. You put it on a little hat and they hold it there, and they have to learn to turn at a perfect rate of 6 revolutions per minute. And from there, you can expand and start doing studies of angular velocity and more. But trying to put kids physically inside the experience of the data makes an enormous difference because, again, they're getting that immediate physical response from data. So let's see, just above the IMU, you'll see a light module that outputs ambient light in lux. It also does color in RGB values, also in lux. You've also got a gesture sensor that's built into that. And one of the things about Databot as well is that it's completely codable. So that means you can program it. Out of the box, again, it's very simple. You can connect to it with Visi. So for new educators or elementary educators, they don't have to do any of the coding, but has tremendous depth for things for people who want to do coding for science. So the gesture sensor allows you to recognize if you sweep left or right or up or down on the Databot. And I'll give you a couple of examples of things like that so that you can see how it works. This is your time of flight sensor. So this is bouncing a laser beam off of an object, timing the round trip, and then determining the distance. So that sensor is good for up to about 2.5 meters. Outputs in millimeters. To the left of the light sensor, you've got an air pressure module, which also functions as a altimeter. We have an activity where kids measure, they do some calibration, and then they physically run up and down stairs, right? And they determine, okay, what's the air pressure change and what's the corresponding altitude change? And they learn about that connection between air pressure and changing elevation. They also learn about calibration and accuracy in that activity. So again, a great type of activity that physically is interacting with data. Whoops, I had that wrong. That's the air quality sensor. This is the air pressure sensor down here. It's labeled HPA for hectopascals. The air sensor is the air quality, which is carbon dioxide. And then down here are volatile organic compounds. So anyway, lots of sensors built in. For physical computing, it also has some attributes. It's got 3 RGB LEDs plugged into it here so that you can basically make it light up like a Christmas tree. You can have it respond to sensor data. A very simple coding challenge, for example, is to create a CO2 alarm, where when you breathe on it, it picks up those elevated CO2 levels. The lights might flash yellow if it's above, 1,500 parts per million, and it might have a beeping sound. If you go above 2,000 parts per million, maybe they start flashing red and they start issuing a little siren sound from the tone generator. So simple things like that allow kids to start coding and interacting with the sensors in a new way, using computational thinking to solve problems. We have some wonderful activities that kids and educators are doing by combining those things. Over here on the left-hand side, this is important. We've got 2 temperature probe ports, so you can do 2 simultaneous temperature readings using these external probes. Again, so it's very convenient. So you can monitor 2 separate temperatures. And the temperature probes are waterproof. Databot is not, but the temperature probes are, so you can drop those into a beaker or a stream. On the right-hand side, you've got I2C and UART. So for those of you who are involved in electronics, you'll know that I2C is a communications protocol, very common. There's lots and lots of sensors out there that use the I2C protocol, which allows us to connect to external devices. For example, we've got a new sensor that we're about to release that is a new UV sensor that reads all 3 bands. It does UV A, B, and C, all with one sensor. And we use that port to connect to it. So we have these adapter cables that allow those of you who are interested in, doing your own types of sensors. We have a lot of tech teachers that do this. We have these cables that allow you to use those ports. There's jumpers that go right to header pins or into a breadboard so that you can adapt your own systems to it. But I2C, again, very popular, and lots of fairly inexpensive sensors that you can integrate with Databot. The UART port, of course, is a serial protocol that allows you also to connect to other devices, which I'll give you a few examples of here in our blogs. So yeah, that's a quick tour of the hardware. The other things I'll point out is that it's an ESP32 processor. For those of you familiar with that, it has both Bluetooth and Wi-Fi built in. So when we use it with Visi, you're using Bluetooth to connect immediately and have that real-time experience. But Bluetooth, of course, has some limitations for range. So you can only use it within, the distance that your device is going to be able to connect. So since it has memory on board, you can code it to actually store memory and data on board, treat it as a data logger. So when people send it up, for example, in a high altitude weather balloon launch, it can collect data locally and you can retrieve it afterwards. We have people sending it up in high power rocket launches, the same scenario. So also putting it out into remote environments where you want it to collect data remotely. And then with Wi-Fi, you can put it out on a network and use it as an IoT device where it's collecting data and publishing that to some kind of a cloud service. I'm going to exit out of this for just one moment, and we'll take a look at a few examples of that so that you can actually see. So let's see, on our website, we have a section called the blog. And for those of you who have been on there, you can browse through there and see lots and lots of different examples of types of things that people are doing with Databot. But let's see, I'm going to look for a specific one here on just IoT. Here's an example of using I2C to add on, for example, a display. You'll see lots of references to IoT platforms like IFTTT. ThingSpeak is another one. This one is one called Adafruit's Ada Cloud. A lot of these services are free, so educators can use them very inexpensively, but they are limited, of course, if they're free. So you can usually only do a few channels or a few cycles with them. But this will give you a good example of how you could use Databot for gathering remote data. Now, this one is a remote smart greenhouse project. You'll notice this dashboard is showing soil temperature, air temperature, humidity, ambient light. And to do that is quite simple. The first half of this blog shows you how to set up MQTT, which is a communication protocol that allows you to communicate with these various IoT platforms. MQTT is a very common protocol. So we walk through how to set up your service at Adafruit. And then I'm going to jump down here to the bottom just so you can see just how simple it is to actually create an IoT solution. So our coding platform is called Microblocks. If I have time, I'll give you a quick demonstration of that. But here's the complete stack of code required to actually create an IoT solution. So here you'll notice, and this is block coding for those of you who have done Blockly or Scratch. Microblocks is something that's very similar. Kids can typically cross over into Microblocks very easily. But I'm going to walk through just this little code stack so you see how it works. So when started, there's a little start icon you click on to start the program. It'll initialize this sensor, which is our light sensor. And then it's going to do a brief wait. You'll notice it's connecting to your local Wi-Fi network. And then it moves on to connect to the MQTT service. So if it's on the Wi-Fi, okay, and it can get to this IoT platform, it'll connect to it with MQTT, checks to see if it's connected. And then if it is, it's going to run just this little loop, and it's running one of the temperature probes here. So it's that easy to be publishing data out to an IoT service. Scroll down a little bit here. And this is an example of a widget that is available on Adafruit. So there it's publishing your temperature value. So just a quick example of how easy it is to use the Wi-Fi and capabilities of all those sensors in an IoT solution. Next thing I'm going to show you here. Let's see, let's go back up here. Oh, this is a good one. Since this is loaded, I'll show it to you real quick. We have lots of schools that, of course, use Lego robotics. And we have a number of space educators who are using Lego robotics plus Databot to teach concepts in space. So, for example, this is the transit method for identifying exoplanets. And this is a very simple model where you create, an orbiting exoplanet in front of a light source, and then you're using Databot as the receiver over here on the right-hand side. So it's scanning, of course, for changes in light intensity. Lots of examples of that kind of activity that educators come up with. All kinds of interesting devices for illustrating concepts in science. This next one I'm going to show you is a good example of coding, and this is using that gesture sensor that I showed you. So again, if you sweep left or right or up or down, it'll recognize it. And the coding here is very simple, but it's a great example because what it does is it recognizes the gesture, and then it's going to change the color of the Databots. So this little video that I'll play for you is a number of Databots that are laid out. They're spelling the word Eid. This was a greeting card we did for Eid last year. And you'll notice as a ruler sweeps back and forth over the Databots, they're going to change color. You have very simple coding. That stack of code is very small, not much larger than the one that I showed you for the IoT. But once kids start to learn how to control the sensors and interact with a coding environment, it becomes very powerful. I think what we'll do now, so we'll jump back over here to our presentation. And I'll explain a few more things here for you before we actually try out Visi. We have about 25 minutes left, and Ninja Physics takes about 10 minutes for you to experience. We're going to install the app and try it. But this is an overview of what I call the sensor ecosystem that's out there. And I'm sure many of you have used a lot of these products over here on the right-hand side, things like Vernier sensors or Pasco or Data Harvest. You know, they're more expensive. They're a traditional approach to labware where you're conducting, you know, traditional experiments, gathering data, and having kids analyze them. On the left-hand side of the ecosystem is your physical computing products. And some of you may be working in those areas as well. So things like the microbit, which is ubiquitous. I mean, lots of people are using that in many, many ways. It has a few sensors on it that'll allow you to do this coding for science, which is similar to what I was just showing you with Databot. So those are fairly inexpensive. There's Arduino in the upper left-hand corner. So the interesting thing about Databot is it crosses both these ecosystems, right? You can use it for conducting traditional lab experiments, but you can also use it for physical computing. And its footprint allows you to do a lot of unique things like I've been explaining, you know, physically interacting with the data in more ways than, you know, typical probeware is going to facilitate. So again, it's a different approach to education. It's a different approach to getting kids familiar with sensors and scientific concepts. You know, our goal ultimately is to have Databots very familiar with, you know, teachers and students at all levels. You know, we've got kids as young as kindergarten that are being introduced to them here in the United States and doing things like that activity I was showing you where you breathe on it. I had a kindergarten teacher create little volcano examples with cups, and she put baking soda and vinegar in one of those cups. So it was emitting, you know, carbon dioxide. And she read a story about volcanoes to her class, and then talked about the types of things that, okay, how do we identify volcanoes? Well, they're giving off gases, right? Things you can't see, but we know that they're a volcano because of that. So then she has the kids take the Databots and they put them over these different cups. So it's like a little mystery, you know, which one of these is actually the live volcano, and the kids identify it. And she has a section in her kindergarten class where she calls it science time. So they all put on little white lab coats and they conduct science. But if you imagine those kids, you know, they're starting here, you know, it's 5 or 6 years old, and they're exposed to Databot and sensor collection at a very young age. You know, think about, okay, it's 2nd grade or 4th grade, you know, continuing to be exposed to Databot, and then I'm starting to be introduced to coding. You know, by the time you've experienced, you know, that kind of exposure to easy access to data and sensors, you know, by the time you get into high school, you're going to be extraordinarily comfortable with the technology, and you'll have had a lot of real examples and experiences of data that surrounds us. So it's a much different approach, and I love it because I've had the good fortune to work with kids at all ages, and I see the reaction to kids, and I see, you know, how it basically scaffolds over time. So it's an exciting approach. I think, you know, you'll see a lot of examples in this. This presentation has, I think, about 18 slides at the end of it that show different case studies of how teachers are using it. I'll share this entire presentation along with that research paper, along with the Ninja Physics lesson so that you can all experience it. Okay, so now we've got about 20 minutes left, and I wanted everybody to have a chance to experience Ninja Physics and then ask some questions. So what we're going to do is, if you have a smart device, I'm going to have you go out to your smart store. You need to go to your App Store or your Play Store. This will work on either Android or it'll work on iOS. So take a minute to look up an app called Visi. It's VIZEEY. It'll look like a very colorful little rainbow colored V. And VISI is for visualize data. Now I have a little video on the website. You literally should be able to install this app if your connection is good. You should be able to download, install it, and be up and running in about 60 seconds. And then once that is done, I'm going to give you a QR code to scan, which is going to bring in some experiments for you. So while you're looking that up, I'm going to exit out of this presentation and I'm going to pull up the QR code that I want you to scan. There we go. Now we're on our VISI website. We're about to do Ninja Physics. So hopefully you've managed to install VISI. And this one on the left-hand side, you see a QR code. When you open VISI up, you're going to see a plus sign on the welcome screen. You want to make sure you scan through VISI and not with your camera. Your camera will just try to download the file. But from VISI, you should see a little plus sign on your screen. You tap on that, and it's going to give you an option for scanning with a QR code. And you're going to want to scan this one on the left-hand side. It's called Ninja Physics, the smart version. And it's the smart version, of course, because you're going to be doing it with your smart device instead of with the regular Databot. Give everybody a moment to do that, and then we're going to switch to the actual lesson plan, and we're going to give it a try. Now, for any of you who've had problems or can't get it installed for some reason, I'll send this entire lesson plan along so that you can do it at your leisure. This is a fun activity to do with kids of any age. I do this with adults. So if you're teaching, college physics, this is a great fun activity to get kids involved in looking at, a visualized force of gravity, and also to discuss, the nature of acceleration. So, okay, I'm going to jump from this. Hopefully you've all gotten this QR code. If not, you should be able to go to just visi.com and it will be there for you, as well as a bunch of other QR codes. So once again, I'm going to stop sharing and we're going to open a PDF this time so we can all do Ninja Physics together. And there we go. You should see a PDF now. And I'll see if I can open that up a little bigger. There we go. Zoom in a little bit. There we go. So now Ninja Physics, this lesson plan has 3 main activities in it. We have what we call PDQs, which are pretty darn quick. Those take about 5 to 10 minutes to do. And then we always have a longer experiment. And in this case, it's the Ninja walk, where kids are going to learn more about acceleration. And I'll explain kind of the progression as we go through it. But the lesson plans are pretty standard. They're going to give you background on acceleration, on the sensor itself, give you some terminology, learning objectives, and we're going to jump right to the actual activity. So now if you have your scan came in correctly, you should have 4 icons that are displayed on your VISI app. And the very first one is called 3D Basics. And I'm going to go ahead and open it up on my phone and just walk through it with you here. So 3D Basics is a free-form exploration of the 3D Cartesian coordinates that I was talking about earlier. So I'm opening it up here on my phone. When you tap on that, it should come up with this screen here. You tap the little start button at the top, and that'll start streaming data. Now, if you're doing this with Databot, it's the exact same process. It's just going to be streaming it via Bluetooth instead of accessing the sensors on your smart device. Another aside on Visi, just so you know, there's a smart experiment option that allows you to actually create your own experiments using your smart device sensors that you can all play with afterwards. Anyway, I'm starting mine. I just hit my little play icon and I'm holding my phone out. So if I'm holding it flat in the palm of my hand, here on the left-hand side of the screen, you're going to see your X, Y, and Z coordinates displayed. If I hold it flat in the palm of my hand, I'm going to see something getting close to 9.8 meters per second squared on the Z axis. So again, this is a great way to get kids physically interacting with 3D Cartesian coordinates. If I look at the Z axis, it's up and down. Now, if I want to see the force of gravity, 9.8 meters per second squared again, shift to the Y axis. I just rotate my phone upright and you'll see it on the Y axis now. If you rotate from there left or right, you'll see it shifting to the X axis. So in the United States, we have a set of standards called the Next Generation Science Standards. And one of the core standards for kids is to understand that, okay, there's this invisible force of gravity, right? And it's a force that's dependent on mass. But as we stand on the planet Earth, the mass of the Earth is pulling all of us and everything around it directly towards the center of the Earth at that gravitational constant that, of course, is based on the mass of the moon. So you're seeing that 9.8 meters per second squared, and you're actually physically experiencing it. And as you move your phone around, you'll see that indeed that force is shifting. It's always pulling straight down towards the center of the Earth. So a good example of physically interacting with data. So if you've finished that form exploration is great just for learning the axes. So now what we're going to do is you tap on the little back button up here in the left-hand corner, and it'll take you back out to your main menu. Now we're going to do the second activity, which is called a steady hand. This is where you start to gamify some of the physics concepts. In this case, we're going to have the kids, it's a timed experiment now. So at the top of your experiment of steady hand, you'll notice there's a little number 3 to the left of the start icon. That means it's a countdown. So it's going to give you a 3-second countdown, and then it's going to start timing. It takes a 10-second data set. And the fun part of this data set, of course, is it's going to score how steady your hand is. So this is where our ninja physics competition begins, folks. How steady can you hold your hand? And of course, you're trying to focus all of that force of gravity, that 9.8 meters per second squared. You're trying to focus it as much as possible on the Z axis. So if you jerk or you wiggle a little bit or you move it upright, of course, it's going to shift it off. And then over time, it's going to take a 10-second data set and it's going to calculate a score based on your largest variations, either positive or negative, and also based on your overall average. So go ahead and give that a try. It takes about 10 seconds. At the top of the screen also, you'll notice there's a little trash can. So once kids kind of figure this game out, it's very easy to delete your data set and do it again until you refine your ninja skills, of course. Now in the chat section, by all means, put your score in. Let's see who's scoring well as a ninja. It's not unusual to score in the 60s when you first start and be in the 90s after you've played it a couple of times. And one of the neat things about this, of course, you know, kids are already interacting with the force of gravity and they're understanding those 3D Cartesian coordinates, but they will never forget 9.8 meters per second squared either because they're staring at it over and over again. So a great example of an introduction to the force of gravity. So we've got a few minutes left. We're going to do the second activity, which is called a smooth walker, and then I'll explain the last one, which of course you can do on your own with the lesson plan that I'll be sending along for everyone. So smooth walker is kind of the next treatment of acceleration, okay? So now we've learned a little bit about acceleration due to gravity. The phone is acting as a force sensor and you're able to see that. Now what we're going to do is look at just pure acceleration. And this introduces kids to the fact that, hey, I can be moving and have zero acceleration. So the idea here is to hold the phone flat in the palm of your hand. And again, it's a timed experiment over 10 seconds. It's going to give you a 3-second countdown. And over that 10 seconds, you need to be walking in a straight line. So you walk for 10 seconds as steady, as smoothly as possible so that there's no interruption. There's no change in the rate of speed, basically. So this introduces kids to the fact that, okay, acceleration is a change in a rate of speed. And if I can be moving at a perfect rate of speed where there's no change, I will be walking with zero acceleration. Now, of course, you have to be a very masterful ninja to be able to do this. It's a lot more complicated than holding it flat in the palm of your hand. But now you're doing two things, of course. You're holding it flat in the palm of your hand so that the force of gravity is focused on the z-axis. And you're moving along the y-axis, trying to move with zero change in your rate of speed. So another great introduction to a very important concept of acceleration. Lots of people still don't understand that you can be moving and have no acceleration when I start this activity with kids. So that's a very fun one as well. It's going to score you. We'll see how you do. And then I'll just explain the last activity because it's more involved. It takes, probably 15 minutes or so to set up and have the kids do. But it's called the Ninja Walk is your final activity. And in the Ninja Walk, you're combining both of these things where the kids have to navigate a field. They have to go through 3 data points. And in this one, it's even more complicated because you're trying to move with zero acceleration on the y-axis. You're trying to balance the force of gravity on the z-axis. And now you have to change direction. So this introduces the second part of acceleration, of course. It's not just a change in the rate of speed, it's also a change in direction. It becomes very, very challenging to actually navigate through 3 points and change direction and hold it flat in the palm of your hand and try to minimize acceleration. So again, this is a great exploration of acceleration all around and a fun activity. So it's a good example of, again, how we design projects so that kids physically interact with these concepts. So again, I'll send this whole lesson plan to all of you. There's also a teacher's guide and a math extension that shows you how the scoring is all done, which is kind of a fun extension for kids who are doing the math. And let me jump back to our presentation here. And I'll just show you the rest of the presentation here, which we'll be sending along since we're about out of time. That'll give us time for a few questions and answers. So we left off on this slide. There are 2 main software platforms we use, Vizy, which you just got to experience, and then also Microblocks, which is the coding environment. Now, Microblocks might look like a simple block programming environment, but it's very powerful. It has all kinds of libraries that have been added to it to support multiple hardware platforms, do things like IoT. So I strongly suggest people take a look at it. It's actually by one of the original developers of Scratch. So John Maloney was one of the leads on the Scratch project, if you're familiar with it, and worked there for over 10 years at MIT. And then he started the Microblocks project because he wanted to create an environment that was really optimized for physical computing and that would minimize download fatigue for kids so that younger students would be able to continue coding without having to wait for that whole compile, download, test cycle. So it's a very real-time, very fast coding environment. Now, beyond that, Databot is very open architecture. So we provide all the Arduino libraries, Python libraries. So we have people doing all kinds of advanced things with it as well, both in data science, teaching machine learning. Lots of different interesting things going on with it. And then I'm going to jump down here real quick. There are lots of lesson plans on our website that you can go to. We have a series called Sensor Starters that are these activities that I was describing. There where kids physically interact with data. At the end of this presentation, you'll see lots of case studies of how people are using Databot in the classroom. which should give you some great ideas. And then there's also some references to other things, here's a good example of an advanced project where you're using IoT to control a smart greenhouse. You can also use it as a controller. So we have people that control complete systems like, a smart greenhouse where it's monitoring various environmental conditions, running a pump when the plant gets dry, things like that. Integration with drones and other technology. Anyway, lots and lots of things. So I'll send this whole presentation over to you all so that you can explore in more depth. And of course, Ninja Physics. And then by all means, you can reach out to me directly at any time to ask questions or learn more about Databot. So let me go ahead and stop my sharing at this point, and I'll open it for any questions. I think we've got a good 7 minutes left. So by all means.
So,
So the house is open for the questions. Anybody wants to ask the question can ask directly or write it in a chat box.
thank you, Robert, for a wonderful presentation. What I was observing was that it's basically targeted to schools, isn't it? Maybe middle school students and maybe K-12 students, up to that range only. And it depends a lot on, once it comes in one's hand, that how one wants to really explore it. The examples which you have shown, they tell us that in which direction we can go and start looking at its usage in various situations for a particular subject or the topic which we are trying to teach in the classroom. Am I right about it?
Yes, our specific focus has been K-12, and we do have universities using it, but that's not been our focus. But as more people get involved with it, obviously, I think we're going to see a lot more use in college classrooms. But yeah, our primary experience has been with younger kids and, basically transforming the way people are interacting with sensor data, making it more engaging and opening the doors for teachers that normally have never been exposed to these kinds of things.
So when you were talking about acceleration due to gravity, I was just wondering that suppose I start from the ground floor of a building and go on top, will I be able to see the change or the difference in acceleration due to gravity which I experienced there? I mean, that kind of a sensitivity we can have, or it will just be around 9.8 always, and that's it.
No, so you have the ability, there's an experiment in the main set called linear acceleration that removes the force of gravity from the calculation. So you can see pure acceleration on all three axes, or there's a absolute acceleration as well that combines all three of those. So you have one acceleration value. So yeah, there's lots of, all of the sensors that are on board. The data sheets are all on our website, but they're all industrial level sensors. They're highly accurate, and you can do all kinds of amazing things with them. They're being used in industry for all kinds of things, ranging from cell phones to automobiles.
One thing which I was really finding very interesting was that greenhouse sensor which was there, using it as a aid for my little garden and try to see that how soil is, having the right kind of moisture in it or not. So I think that was very interesting. I can carry it in my pocket and I can go into my garden and try to check all those things. So that was very exciting for me. That let me at least do those things with the help of it. Interesting.
Yeah.
Yeah.
And you can share with us those papers which people have published, because I saw some PER people, a lot of PER people have used it and written papers on it. I was able to see Sokolov's name, one of the papers there.
Yes, I'll share all those in the follow-up email for you all.
And I have a question, like Robert, what is the cost of this device which you are showing, and availability of this device? Is it available? Yeah.
Yeah, they're $189 US.
Mhm.
What is that, about 15,000 INR, I think, somewhere in that range. And yes, they are available in India as well as in the United States. We actually have offices in India located in Bhuj, so we have local support and inventory.
All right. Thank you. So, any other question? If anybody wants to ask a question? Govind sir?
Yes.
Dr. Satya, would you like to really ask something? You can unmute yourself. I hope he's there. Yeah. I can see him in the gallery.
Yeah, he was there.
Can you hear me, sir?
Yes, yes. Yes, Satya sir, we can hear you.
Yeah, please speak.
Can you hear me, sir?
Yes, definitely. We can
Yeah.
hear you.
Yeah. First of all, thank you very much, Robert, for excellent presentation and the excellent work you have done by gathering so many sensors and combining in a small data pot. So the demonstrations you given are also excellent, and I understand this is very useful for the students at elementary level to introduce. And you also talk about the micro blocks programming. This is also very interesting. Only thing is, Sapna madam is already asked, so how to get this hardware in India? Maybe you can work out on that thing. If it can be easily available, then maybe in India also we can try introducing at the elementary school level. So this is my, query from you. So you make it available in India, maybe with the help of anyone, so that maybe this physics society can get benefit
Benefited, yes.
by using at the elementary school level. That's it. That's what I want to.
Yes, it is available in India now. In fact, it's carried by several of our resellers. EduTech India carries it. It's being used by Creya Learning in a number of programs. What's the name of the other company? There's a company called Technoscience that carries it as well. And then you can order it direct from our website. We have an Indian website, just databot.in. So we have local inventory in Bhuj, which is in Gujarat. So you can order and use Databot locally. We've also got a wonderful science communicator. Her name's Sakshi Baid, that is available for local support and training.
Thank you very much.
There is one more question in a chat box. Mr. Robert, it says Maya Iyer is asking, can we add more sensors to it ourselves? If yes, how?
Yes, that's a great question. Now, if you remember, there's the two ports for expansion. One's UART and one's I²C. And lots of people add on the I²C sensors. So if you're familiar with the Arduino ecosystem that's out there, there are a lot of I²C enabled sensors. And what it allows you to do is use the existing Arduino libraries, connect it basically to Databot, and access that sensor data. There's actually a blog on using Databot as kind of a universal sensor for Arduino, which you can take a look at and basically see the approach. But if you're familiar with coding, you're familiar with the Arduino world, you would be able to adapt sensors very quickly and easily. And again, we have these adapter cables, which I think they kind of fuzz out when I hold them up. But they have a micro USB connection on one end that plugs into the Databot, and the other end has either female header connectors, so you can connect it directly to header pins, or the other adapter cable has male connectors that'll plug right into a breadboard, for example. So we provide a lot of tools for you to adapt your own sensors. And then, of course, we're always working on adding support for others as well. That UV sensor I mentioned is going to be available this month, actually, for teachers to start using.
Robert, one thing more which I wanted to ask is, are the people who give it in India, they are the resellers, or they are also manufacturing it in India? Because the cost can really come down like anything if it is manufactured in India itself. Because at the moment, the cost is around 20,000 rupees. I was trying to roughly calculate it. So that means that it's at the cost of, say, a typical smartphone. That's how it is costing in India. But if I buy it as an add-on kind of a thing, which is being used with a smartphone itself, the cost suddenly goes up to about 40,000 rupees, and that is around $400. So is it being made here in India also, or it is being only reselling is done?
No, it's actually made in India. And, there's a variety of software that allows you to use it, not just with a smartphone, but with any device you might have. So if you have a computer or, Chromebooks are used extensively in the US as well. So it not necessarily requires you to have both devices because you can use whatever you have. But yeah, it is manufactured in India now. And that is, I understand what you're saying. If we had to import it, it would be considerably more expensive.
Because you showed us a graph on which you had put it at $179 cost. And then you had given us a range as the sensors were improving, and it went right up to around $1,000 in that graph itself. So still, I think we can try to, so these Bhuj people are actually manufacturing it in India?
Yes. Mm-hmm. Yep. We actually own an Indian company, and then we do contract manufacturing for the PCBs and assembly in Ahmedabad and Bhuj, and we also do the plastics in Mumbai. So yeah, the product is primarily manufactured in India.
Okay, thank you.
For the Indian market, yeah. I see another question about industrial purposes. And, we don't recommend it for industrial purposes, but we do have people using it for that, for air quality monitoring and things like that, because the sensors that are built in are exactly the same sensor that are being used in a lot of industrial applications. But that's not our focus, but of course you would be able to do whatever you want with it once you have one.
Okay. So there's no more question in the chat box, and if anybody wants to ask the question, we can still have. Yes.
Yeah, most of the sensors used here is, I think, visible light sensors. Is it true?
Yes, the current sensor that is used for light is the APDS 9960. So it reads visible light, ambient light, and RGB. The UV index sensor that is on board will read just the index. And then we have an external sensor that's available this month that actually reads UV A, B, and C.
Okay.
So we don't have any question in the chat box, but there are comments like it's excellent work and congratulations to Dr. Robert. So thank you, Mr. Robert Grover. I don't think so. We'll have more questions. Anybody wants to ask the question, please come forward, or we will just close it.
Govinda, would you like to really comment on it, because you have been using it, you have got that device, and how do you find it? How are you using it?
Yes, sir. I have got this last week only. Actually, this was given to one of the exploratory in Nagpur. And I connected this with my smartphone, and it is working very nicely because in our smartphones, we have limited sensors. Here, I can see CO2 sensors, even color, gyroscope, humidity sensor, inclinometer. So with this, I think, sir, one can easily enter into the UG grade research activities with our undergraduate students. So there is a huge possibility that we can really utilize such kind of device in our teaching learning program. Even we have seen that Shokolov has also published one of the research paper over this, who has also delivered one of the session in our PR series. So
Yeah.
I'm looking forward to explore more about this.
Right.
Yes. There is another question. How far sensors can be connected? Maximum distance through cable or Wi-Fi? Mr. Robert?
Let's see. So with Bluetooth, your range depends on your device. We've had Bluetooth connections that are anywhere from 10 meters to literally 100 meters. I've had some devices that will actually connect over a long distance. Now, Wi-Fi, anytime you're within a Wi-Fi network, of course, you can have it on that particular network. So that'll just be dependent on your Wi-Fi. Not sure about cabling. Normally, if you're going to go beyond any long distance, you would actually store the data locally, because you've got, I think after the firmware, we've got close to 2 megabytes of space for storing local data. So for example, if you were collecting, let's say you were collecting environmental data, and maybe you were collecting light, temperature, humidity, carbon dioxide levels, volatile organic compounds. Let's say you were taking samples of those every minute. You literally would be able to take, months worth of data with the available memory space. So I don't know about cable length, but for storing things on board, you've got lots of capabilities. Quick response time. I see another question there. Yeah, it's again, the sensor data sheets are on the website, so they're pretty much instantaneous, which is why that's why it's so effective with kids. Again, you breathe on it and you get an immediate spike. The CO2 sensor takes less than 15 seconds to warm up, and then it's reading data. So the response on all of them is very real time. Same thing with the accelerometer. And part of it depends on how much data you're trying to read simultaneously. So you literally can read all of the sensors simultaneously on the app, but you'll notice that you start to get some latency if you have all of that data trying to be shoved through a Bluetooth connection simultaneously. So it just, there are limits to everything, but yeah, it's pretty quick.
So thank you very much for answering all the queries, Mr. Robert. And I don't think so there is any more question now. So can we stop here?
Wonderful.
Yeah, Govind?
Yes, let me conclude the session.
Yes, Govind, sir.
I would like to express my sincere thanks to Mr. Robert, CEO of Databot, for his insightful presentation. He introduced us to the 16 types of sensors on Databot device and demonstrated the integration of IoT solutions in the education. The classroom demonstrations for K-12 students, along with the Vizi app and Ninja physics lessons, showcased how technology can enhance learning experiences. Yes, the experiment using smartphone sensors was particularly engaging and illustrated practical applications in real time for this device with this device. Additionally, Mr. Robert shared lesson plans and case studies, providing us the valuable resources to implement these ideas in our classrooms. His insights into the scope of research and teaching learning demos remind us of the exciting possibilities ahead. Thank you once again, Mr. Robert, and thank you for your participation in our PR lecture series. Thank you.
Yes.
Thank you for having me.
Yes.
Have a wonderful evening.
Thank you, Dr. Govind. Thank you, Mr. Robert. And thank you, everyone who has joined us today. So with this, we come to the end of this talk. Thank you very much. Have a nice day. Mr. Robert, have a nice day and good night, everybody here.
Take care.
Yeah, thank you all.
Thank you. So Govind sir, thank you very much.